Got it, Katya? Okay. Good afternoon, everyone. My name is Dr. Revin, and I am working as an assistant professor in Department of Applied Physics in IMT College of Polytechnic. Today, I am going to discuss about the superconductivity. My question is, what is superconductivity and how it is useful for us? Superconductive materials are very useful materials, and these are the future materials for everyone. How it is useful? We can get the electrical cables in which material in which there is no resistance. Means superconducting materials are the materials which has no which has no resistance. So we will discuss about these superconducting materials one by one. These are the contents of my topic. First one is definition of the superconductors. Then we will discuss about the discoverer who discovered the superconducting materials. Then we will discuss about the Meissner effect. Meissner effect is the reason of the superconducting material. And then we will discuss about the properties of superconducting materials. And the last one is the applications. We have so many applications of superconducting materials. That's why we are searching for this material. Now, what is superconductivity? It is the phenomena occurring in certain materials generally at very low temperature, characterized by the exactly zero electrical resistance. This is the important term. Means it has zero electrical resistance, means no opposition. Means if we are using this superconducting materials in electrical wires, then there will be no resistance. Means we have to initiate the current, and we can get this current for years and years without any resistance. Means it will flow and flow, means it will not stop. Second point is the exclusion of interior magnetic field. Means there is no, means the electric magnetic field will not move inside this superconducting material. Now we are going to say simple words. For some materials, this resistivity vanishes at low temperature, and they become superconducting, and such materials are called superconductors. Now, question arises, why was it formed? Before the discovery of these superconducting materials, it was thought that the electrical resistance of a conductor becomes zero only at absolute zero temperature, but it was not so. It was found that some materials electrical resistance becomes zero when cooled to very low temperature, such as we have seen in the case of the mercury, that in the case of mercury at 4.2 Kelvin, we will get the superconducting materials. And these materials are nothing, these are the superconducting materials. Even if we use some more materials, means we can make the superconductor of iron, tin, and so many materials. Now, who was the discoverer? It was discovered by H.K. Owens. He is known as the father of superconductors, who studied the resistance of solid mercury at cryogenic temperature using the recently discovered liquid helium as refrigerant. Means he was the first discoverer of this superconducting materials, and he got Nobel Prize in 1911 for their work on superconductors in 1913. And in 1913, we also got another material, means another material, it was a lead. Means in 1913, we got the lead at 7 Kelvin and niobium nitride at 16 Kelvin. You can see this graph. You can see this graph of this mercury. When temperature is decreasing, then resistance is decreasing, decreasing, and decreasing. And at 4.2 Kelvin, we get abrupt abrupt change in its conductivity, resistance. Means resistance disappear at this temperature. And at this temperature is known as critical temperature. And at this temperature, it becomes superconductor. Now, what is superconductivity? Superconductivity is the phenomena of losing resistivity when sufficiently cooled to a very low temperature. These are the some properties of superconductors. Zero electrical resistance. Defining properties also. Critical temperature, we have discussed at critical temperature, it become superconductor. quickest test है, it's 10 की power minus 5 ohm centimeter. You can see this graph. This is the graph between the resistance and the temperature. This is for superconductor and this is for superconducting material. You can see this graph and you can see the difference between the superconductor and the non-superconducting material. Now, what is the effect of magnetic field on superconductor? Superconducting state of the material cannot exist in the presence of magnetic field of a critical value, even at absolute zero temperature. You can see this critical magnetic field. Critical magnetic field is the field which is required to destroy the property of superconducting property at any temperature. Means you can see this niobium can destroy its property at 198 Kelvin. The lead can lose its property at 80.3 Kelvin and tin at 30.9 Kelvin. You can see this. This is the formula for critical magnetic field. We have Hc is equal to H naught bracket 1 minus T upon Tc ka whole square, where this H naught is the critical field at 0 Kelvin. T is the temperature below critical temperature and T is the transition temperature. You can see the graph between this temperature and this magnetic field. This is the value of this H naught, means critical field at 0 Kelvin. This is the normal behavior and this is the superconducting behavior of this material. Now, what is Meissner effect? When the superconducting material is placed in magnetic field under the condition, means when it is less than critical temperature and when it is less than critical magnetic field, the flux lines excluded from the materials. Means you can see here under when temperature is less than critical temperature and critical magnetic field and the field is less than critical magnetic field, then these magnetic lines cannot penetrate this material. Means materials exhibit the perfect dimagnetism or flux expulsion. This condition is known as Meissner effect. And this is one of the important property of the superconducting materials. In this case, we have this susceptibility is equal to 1 and the magnetic field is -1. We have two conditions which are responsible for this, for a material to be a superconductor, known as, first one is the resistivity must be equal to 0 and next one is the magnetic induction B is 0 when it is in uniform magnetic field. So these are the two conditions which are used for superconductors. Now we have two types of superconductors. First one is sudden loss of type 1 and second one is the type 2. Type 1 is also known as soft superconductors and type 2 is known as hard superconductors. In this type 1, we have sudden loss of magnetization. Means it can lose their magnetization sharply. But in the case of hard superconductors, there is a gradual loss of magnetization. And in type 1, we have it exhibits Meissner effect, complete Meissner effect. And in type 2, does not exhibit complete Meissner effect. It can show partially. And in this case, we have this critical magnetic field is equal to 0.1 Tesla. And in the case of this hard superconductors, its value is approximately equal to 30 Tesla. There is no mixed state in these soft superconductors, while in the case of type 2, there we have mixed state present in the case of hard superconductors. You can see the graph of this one. Means this is the for magnetization and this is for a magnetic field. If we plot the graph between the magnetization, and you can see this graph. This is the graph for the magnetization and magnetic field. This is the value of critical magnetic field. In the case of this type 2 means hard superconductors, we have such type of graph. Means it has two value of critical magnetic field, Hc1 and Hc2. Now we have several materials which can be utilized as a superconductors. Few of them are given below. Tin. We can, if we are using tin at 3.72 Kelvin, then it can work as a superconducting material. Even this mercury is at 4.15 Kelvin. This lead at 7.1, niobium titanium at 10 Kelvin, niobium tin at 18.1 Kelvin can be used as a superconducting material. So in the case of superconducting materials, the 5 times people get Nobel Prize for superconductivity. H.K. Owens, first one is got by H.K. Owens in 1913. Then John Bardeen, Cooper, and Schrieffer in 1972 get this BCS theory. For BCS theory, they got Nobel Prize in 1972. And after that, in 1973, Josephson, Griever, and Esaki got Nobel Prize. And in 1987, Badnoz and Muller got the Nobel Prize. And in 2003, Anthony Ginsberg and Abrikosov got the Nobel Prize. So 5 times the people got Nobel Prize in the case of superconductivity. Now, these are the few properties of superconductors. In superconductors, one such property is the zero electrical DC resistance present in the material. Means we have electrical zero DC resistance, which is the most important property of this superconductor. Irrespective of the physical properties of material, we have these so many other properties also, such as heat capacity, critical temperature. This is different for different materials. We have the superconductive phenomena has a key role by decrease in the temperature. This indicates the superconductivity in the superconductors is a thermal property, and hence having reached a superconduction state, the phenomena is independent of the physical properties of the materials. All these superconducting materials behave in the same manner. When materials change from a non-superconducting state to a superconducting state, there are significant change in the physical properties of the material, which are the characteristics of the phase transition. When the temperature drops below a thermal superconductor, there is an ejection of the magnetic field, which is known as the Meissner effect. In the superconducting phase, Gibbs free energy of the conductor is lowers the normal non-superconducting phase of the free energy. So this is all about the properties of the superconductors. We have so many other properties also. We have some disadvantages also. Means it has so many advantages, diverse range of applications, but we have some disadvantage also. Means disadvantage is the temperature. Means we can get the superconductors only at very low temperature, and this is the only disadvantage of the superconductor. That's why we are not using these materials as a superconductor in now. The research is going on to make these superconductors at high temperature also. Maybe in future we will get the superconductors. So we have so many applications of superconductors, and these are the super applications of superconductors. We can discuss one by one. First one in the engineering. Engineering, we have transmission of power. Means we can transmit power from one place to another place. Second one is the switching devices, sensitive electrical instruments, memory storage elements in computers. We are using computers nowadays. Everyone is using. Manufacturers of electrical generators and transformers. So these are the important properties for the engineering people. We have other applications in medical also. Means we have application for the brain tumor, defective cells in NMR scanning also, and separate damaged cells and healthy cells. We can use these superconductors. Superconductors can perform a life-saving function in the field of biomagnetism, and it can be used in so many instruments. Last one is the power transmission. We know that if we utilize this superconductor instead of copper wire, that it means we have 18,000 pounds of copper wire will be replaced by 250 pounds of superconducting cables. Means, and there will be no loss due to heat. Transformers can be made smaller and last longer. Annual budget saving of 40% could be obtained with replacement of copper wires with superconducting cables. We can use in the cyclotron also. Cyclotron is a switch that operates using superconducting. The cyclotron works on the principle that magnetic field destroys superconductivity. Now, when the current flows through the tantalum wire, it is superconducting. But when a current flows through the niobium wire, we have niobium wire, okay, when magnetic field is produced, this destroys the superconducting, which makes the current slow down or stop. So it can be used as switches also. Now we can use superconducting chips also. Superconducting processor does not generate much heat. Means we have this chip also superconducting, and this chip is only 4-bit compared to the 32-bit. And now we are using 32-bit or 62-bit processors. But if we are using this superconducting chip, it can only be 4-bit. And this 4-bit is 500 times faster than the today's common Intel processor. And NASA and NSF are working for developing a superconducting chip, and we will get these chips in another 10 years. Now we will get the super motors also. Motors accounts for 70% of the power consumption in the domestic manufacturing and 55% in the entire utilities. Means most cruise ships and large naval vessels are switching to electric propulsion. This is the diagram for the super motors, and these units are quarters than traditional electric motors. Now, magnetic levitated trains. Magnetic levitated means maglev is the form of transportation that suspends, guides, and propels vehicle by electromagnetic force. This method can faster than wheel mass transit system, potentially reaching velocities compared to the turboprop and jet aircraft. Nowadays, means Japan is using this technology in the bullet train. We have heard about the bullet train, and this technology, this magnetic levitated train, is used in the Japan bullet train. Now we can see this diagram and understand the rail and train exert a magnetic field on each other. You can see this north, south, and you can find this train levitated is the repulsive force between this magnetic field which propels the vehicles. Now we can create superconductors then work at room temperatures. Nowadays people are working on superconductors, and in future we will get superconductors which can work at room temperatures. Scientists are currently working on developing superconductors that are closer to room temperature. Means you will get superconducting wires, you will get superconducting chips, you will get superconducting motors which can improve your life, means which will be helpful for the society, which can improve, which would make superconductors which are more important to every day. Superconductors have the potential to carry an electric charge across a infinite distance without losing any whatsoever. Nowadays we are using these cables, copper cables, to transport the electrical energy. But when we will get these superconducting wires, then we can transport our electrical energy without losing the much energy. Means loss will be minimum. If we control in room temperature, it would be possible to transport electricity from power plant on Earth to residential area on Mars. Just imagine this thing. You can transport your electrical energy from your planet to the Mars and create lightning fast computer circuits with no resistance, developing weapons such as quickly reloaded rail guns and transport possibilities such as biohazard free levitated trains. So in the near future you will get all these things with the help of this superconducting materials. So for this, we will have so many other applications also, and we can discuss these applications later on in our next lecture. Till now, thank you very much. Thank you for all for your kind patience.